Hi, my name is AERO320.
And I'm Alec Bluhm, and we did our controls project based on the dynamics of an arcade claw game.
There are three distinct features of the dynamic system. The first feature is a moving claw carriage with a continuous position in the X and Y axes.
The second is a variable claw height, which is actuated via a button press, which is stopped by the signal to the load cell.
The third feature is a two-position claw mechanism with actuation based on signal from the load cell.
The claw is essentially a 3D pendulum, and will follow the equations of motions laid out to the right. These equations of motion indicate stability at theta and phi equals 0.
So as you can see, whenever Alec's left hand actuates the joystick, the carriage has a resulting motion. The claw itself always trends towards a stability position directly downwards. Now, whenever the button is actuated, there will be motion in the Z direction. Now, as the claw drops, the force is triggered, it knows to stop, the claw closes, and it grasps the prize. As we can see, the system itself is clearly a continuous system. There are no defined points in which it just moves fluidly throughout the XY plane.
There are two inputs into the system. The first input is the joystick, which drives translational motion in the X and Y axes. The further displaced the joystick is, the faster the carriage moves.
The second is the button press, which drives motion in the Z axis, which is the claw drop and actuation.
The system has three main inputs that are being measured. The first input being measured in the system is joystick displacement, which as stated earlier drives carriage motion.
The second input is button actuation. This is a square wave as the switch is either on or off. As mentioned earlier, this drives motion in the Z direction.
The last system being measured is the load cell, which takes force from the weight of the claw. When the force is lifted, the claw is touching the objects and therefore will close.
The joystick operates on a closed-loop system. The displacement of the joystick is measured, while actual distance is determined via an encoder.
The claw relies on the button signal for both motion initialization and claw actuation. As previously covered, the signal determines movement in the Z direction, and then a built-in sensor determines claw actuation.
The carriage follows a standard PI loop. The joystick displacement is the standard proportional gain.
The encoder accounts for the integrator, as it counts the error in each step and corrects for it.
There is no predictive error as the carriage does not ever move to a set position via the joystick, which makes predictive motion irrelevant.
The claw has a small set of necessary performance metrics. The claw must have motion in all three directions, while resisting unwanted motion due to residual claw momentum from swinging.
The claw must also be able to close with enough force to pick up prizes. This is still a control, as the force can be directed electronically.
There is only one coordinate frame in this control system. The origin point to this coordinate frame is where the claw goes to rest above the prize drop chute.
The current position in the frame is given by the current claw location, with it always returning to the origin.
The control laws that have been stated throughout the video can be seen in the following block diagrams.
With the block diagram on top, it can be seen that the button actuation controls the claw position in the Z axis. After hitting the end condition, the force sensor closes the claw.
The joystick moves the claw position, which is adjusted via an encoder, which results in actual position change. Don't forget to like,
comment,
and subscribe, and don't forget, it's all about the turtles.